Pretty long, right? But what does it do? The most important thing is to understand what does it do. What is the meaning of phase estimation? That is more important than understanding the matrix, right? So let's take a look at this. For any unitary matrix. And why do I care about unitary matrix? Because all our quantum gates are unitary, right? And we call it U. Its eigenvalue must be unity. And that is one reason why it's called unitary. What does it mean? What is the meaning unity? It cannot be just one, right? It's e to the power I 2 pi times a phase factor phi. Okay, the eigenvalue for any unitary matrix must be in this form. Okay, I can prove this to you. Proof. I know that the unitary matrix times its eigenvector must be equal to its eigenvalue times its eigenvector, right? And then I can write its bra equivalent form, which is this. Do you remember this? Right? Because this form, what is the bra form? It must be the bra of lambda times the adjoint of U, right? And this was column matrix, this become row, so that's why your matrix, column vector, this become row, matrix need to go to right. Same for is any scalar, U becomes the complex conjugate, vector becomes the bra, right? I hope this is easy for you. Any questions? Just the dual space correspondence that we learned earlier. Okay, let me say one more time. The cat becomes the bra. The matrix becomes also matrix, but the adjoint matrix. Scalar becomes complex conjugate. Vector becomes the bra. Right now and then I multiply them together. This is 1, this is 2, and then 1 times 2, what this is? Lambda, U dagger, U, lambda, equals to lambda, lambda star, lambda, lambda, right? And let me say here, otherwise when you review, you will forget. Lambda is the eigenvector, right? And lambda itself is the eigenvalue. Is this okay? I just multiply this by this, must be equal to this by this, right? But what is U dagger times U? Identity, very good, because it's a unitary. If it's not unitary, it is not. And what is lambda times lambda star? Is the magnitude square, right? So what does it tell us? Its magnitude must be equal to 1. So it's on the unit circle of the complex plane. So it must be in this form, e to the power I pi theta phi, right? Is that okay? Lambda is a complex number, and its magnitude is 1. Then this must be on the unit circle. On the unit circle of the complex plane, right? So this is a proof. Now this is important because if all the matrix is unitary, all the gate is unitary, I will be interested in understand what is phi. If I know the phi, I know the eigenvalue. Okay? So what does it do? QPE, quantum phase estimation. QPE is to estimate, right? We want to calculate, but unfortunately, there's some approximation to estimate the phi of the eigenvalue of a matrix of a gate. Okay, let's take an example. For example, I have this gate, phase shift gate pi. What is that? 100. What is the phase shift gate pi? What is that? E to the power I pi, yes, minus 1. Okay, and it happened that what gate is this? Which gate that we are very familiar with? 100 -1. C gate. Yeah? Turn out this is C gate, right? Now, this is not useful for me. That's not why. I want to know the eigenvalue of C. What's the eigenvalue of C? You know already, right? 1 and minus 1. And this is in diagonal form. Remember? When your matrix is written in diagonal form, all elements on the diagonal must be eigenvalue, right? So I don't need to find the eigenvalue. But I will go to represent it in this way. E to the power I 2 pi times 0. E to the power I 2 pi times negative pi over 2. The reason is that I want to make it into this form, right? So e to the power I 2 pi 0 is 1. E to the power I 2 pi negative pi over 2, no negative, right? Actually, this is just I. This is just I. Give me, and also I don't have 2 pi, I'm sorry. Just 1 over 2, right? Is this correct now? So, I have two phases. The first phase for the first eigenvector and eigenvalue is equal to 0. The second phase, which is for the second eigenvector and second eigenvalue, it's 1 over 2. Okay? So the quantum phase estimation is to find out 0 and 1 over 2. Okay? That is the purpose of the quantum phase estimation. Right? I give you an example. In summary, any unitary matrix has all its eigenvalues are unity. They must be in the form of e to the power I 2 pi phi. And my goal is to find out what is the phi. And there are many phi, depends on which eigenvalue you are talking about. How many eigenvalues do we have for n-dimensional space? Just n, right? Because when you diagonalize it, all the diagonal elements are the eigenvalue, right? So you have n of them. So I can find n, the phase of the eigenvalue. And why it is called phase? Because they all represent in the form of e to the power I 2 pi something. And we are not calculating e to the power I 2 pi phi. We are calculating phi, and we call it the phase. That's called quantum phase estimation. Is this okay? Yeah. Oh, no. Okay. Phase is phase. Quantum phase is just talking about this is a quantum algorithm. So this is still just a regular phase. It's not something called quantum phase. I try to estimate the quantum phase. But it's a quantum method for phase estimation. Okay. Unfortunately, this is the... Okay. It's just like quantum Fourier transform. Okay, still Fourier. Yeah, otherwise he would be unhappy. You put another name to his last name. It's a quantum way to do Fourier transform. Okay. That is an example of quantum phase estimation. Now, our goal is only look at one example and understand how each qubit evolves along this process. And you understand how to calculate And then with this knowledge, you will be able to understand, for example, the HHL algorithm, which can solve the sparse matrix for a system of linear equation exponentially faster, right? So this is just, we are not proving it. No, actually, we prove it. You can prove it. Look at my test book. Once you follow this simple example, you can prove it easily. Prove that this is right. We can find the phase. But we did not try to derive it, right? Just like the quantum Fourier transform, I did not try to derive it. What is in this circuit? Let's talk about what if I want to estimate the phase of C gate, right? C gate is a matrix. Then how do I estimate it? You see that I have two groups of register. The top group, I call it the B register. And the bottom group, I call it the C register. Again, LSB on top, MSB at the bottom. Okay? Now, in the bottom, we always input 0. Okay? Just 0. The ground state. Maybe I just say this is the ground state of the system, right? Everything is 0, the lowest energy state. In the B register, we input an eigenvector. Now you will say, so you do need to know the eigenvector in order to estimate the phase. But you do need to tell you which eigenvalue you're trying to estimate, right? So you put in the eigenvector, I find the eigenvalue, the phase of the eigenvalue correspond to this eigenvector. That is the purpose of this. Not very useful now, but later you remember we can have superposition. Then I could estimate all of them at the same time and then play with this constructive and destructive interference trick in the HHL algorithm, which we won't cover, but that is what we're doing, right? So you say, okay, two inputs. Top is the eigenvector, bottom is the ground state. Now I want to ask you, how many qubits do we need to represent the eigenvector of the C gate? Or basically, how many qubits does the C gate operate on? Only 1 qubit, right? So its eigenvector, we also can just use 1 qubit, right? We actually know what the eigenvector of C gate is already, right? E0 equals to 1, 0, right? E1 equals to 0, 1. We already know that, right? This corresponding to the lambda equal to 1. This corresponds to the lambda equal to -1, which corresponding to the phase equal to 0, corresponding to the phase equal to 1/2 that we just show here, right? This gives you -1. This 0 gives you 1. Is this okay? Yeah.
So the first thing here, E is 0. That's a 0, and 1, 0, 0. The reason that corresponds to 1 is because when diagonal lines.
This is, do you remember when you find the eigenvector of the C gate? Yeah, you can say diagonal lines, or you find the eigenvector, use the matrix form, whatever. When you come up with the eigenvector is 1, 0, the corresponding lambda is 1, right? And we can prove it easily, right? This. Yeah, this is something confusing, right? But that is the case because 1, 0, 0, -1. This is the matrix, right? Times 0, 1 in D equal to -1 times 0, 1. Yeah. So this is, so sometimes I talk about energy, so don't think about that because you need to think about whether it's electron or proton, because the charge is going to affect the spin relationship between the spin and magnetic moment. So this is confusing, I know, because we keep thinking that this looks like at higher states and then you have a lower energy. But we still have not take all those magnetic moment into picture. It can be a higher energy if this is an electron, right? Negative charge, right? But anyway, that is good point, right? But this is the one eigenvector. This is another eigenvector. The corresponding eigenvalue is 1 and -1, and the corresponding phase is 0 and 1/2. Our goal is to estimate, but it turned out how we estimate it. I just tell you the answer here. In the C register, we start with 0, 0, right? Eventually, it will store the phase in the form of 2 to the power n times phi. Okay, instead of storing phi, it's storing 2 to the power n phi. But you already know what is n, right? What is n in this case? 2, because I have 2 qubits. Yes, right? So it's 2 to the power 2 times phi. Okay, we store in that way. Right? And that's why here I say this is equal to 2 to the power 2 times 1/2 equal to 2, which is in binary, you will get 1, 0. When you do measurement, you will get 1, 0. Now, do not understand why, do not try to understand why yet, but I want you to understand the structure of this circuit, right? So let me say one more time. The top you put in the eigenvector. So when this eigenvector, the number of qubits must be related to the gate you are going to find, right? The gate you are interested in. This is a 1 qubit gate, so your eigenvector is 1 qubit is enough. If this is this matrix is 16 by 16, how many qubit is that? If matrix is 16 by 16, how many qubit? 4 qubits, right? So you only need 4 qubits for here, right? C register is different. You can put as many qubits as you want. But why it is important? Because you find eventually it's going to store 2 to the power n times your phi. If you only have 1 qubit, you are going to do 2 times phi. Your resolution will be bad. Because your phi can be 0.123 or 0.01. Both of them, when you try to multiply by 2, they're close to 0. You cannot resolve that. So you want to have more qubits so that I have 2 to the power 10, it means 1,000. Then I can resolve very small numbers, because when you multiply by this, I can have integer. Because the output are integers, they cannot be decimal. So in this case, when my phi is 1/2, because I have 2 qubits, it multiplied by 4, then it becomes 2, I can store it. If I only have 1 qubit, I can also store it actually. If I have 1 qubit, what do I get? I get 1, right? But here we have 2 qubits, okay? So how does this work? This is easy, Hadamard gate. And then finally is the quantum Fourier transform, which already done before. We do quantum Fourier transform on the C register, okay? And in the middle, what is the meaning of this? Can someone guess what is the meaning of this gate? Control Z gate? Control something gate? Now, let's take a closer look. Is this a Z gate? If it's a Z gate, I would just write Z, right? What do you guess what it is? Or very good. C tensor something. But tensor how many times? Tensor by 2 to the power 2 minus 1 time. 2 minus 1 is 1. 2 to the power 1 is 2. So it's just a Z square. So it's just C tensor C. Here is just C itself, because 2 to the power 0 is 1. So do it 1 time, right? So we need to build this control gate of interest, okay? We are finding C gate, then you will do control C gate. If you are finding another gate, let's say called SJSU gate, you invent something. Then you need to control SJSU 2 to the power 2 minus 1, 2 to the power 2, 0. And how do we do this? How many exponent do we need? Now it depends on the distance. If distance is 1, 2 to the power 0. Distance is 2, 2 to the power 1. Okay. So a little bit like the Hadamard gate, but now it's a little bit opposite. This is 2 to the power 0. In Hadamard, a little bit like the quantum Fourier transform. When the distance is 1, you do 2 to the power 2, and anything plus 1, distance plus 1. This is distance minus 1, right? This distance is 1 to the power 0. This distance is 2 to the power 2 minus 1. I mean, you don't need to memorize, just Wikipedia will tell you, right, if you need it. But you know it has this pattern. So now I want to do is go through how the wave function will evolve along this path, and then show you that it does find the phase of the circuit. And that is, you can treat it as an exercise, but that is one of the major purpose of this class. I give you any gates, you know it, how it evolves, then you really understand, you can modify it, you can go deeper, you can learn new things, right? So we will spend time on this. Okay? Any questions?
Yeah, so you always have to start with 0.
Yes. So this is the algorithm. You start from 0. But you see that it actually don't want to start from 0. Its goal is to do what? Linear superposition, right? So it starts from 0 and add the Hadamard gate to get the linear superposition. That is how it, right? And then we see how it works. So let's start, okay? That will be a very exciting exercise. And I have how many slides? I have 3 slides for this, right? Although it looks lengthy, but I think you are all good at this. I hope you can appreciate your ability now. What is Z0? Can someone tell me? 0, 0? That's it? We need to look at the whole system. Yes, everything. Okay, he said 1, 0, 0, but now I want to keep it as E1. Okay, just a name. Okay, so this is right. Yeah. Okay, easy, this one. Okay, after you go through the first gate, right? C1. What is that? Plus E1, very good. Do you understand? Do you agree? But we can do it slowly. We first write down the matrix and apply it to C0. And we know that they just independent of each other. Apply the gates to your space. It's just like the law. Apply the US law to US, Canadian law to Canada. Don't bring your law to here, right? So we apply it, and that's why he said that it becomes plus, and E1. But we want to work on the 0-1 basis, right? So what you're doing is correct, but which has a lot of insight, but we decided still work on the 0-1 basis so that we can see what we want to see later. This is equal to 1/2. Zero, 0, 0 plus 0, 1 plus 1, 0 plus 1, 1. I even don't need to look at it because, as you said, it creates a superposition, right? An equal superposition. And that's it. Then we arrive the C1, right? Before we proceed, we need to understand what is the matrix form for the control C and the C, right? So we do it one by one. This is easy. C to the power 2 to the power 0. Okay? So for those who want to leave now, you can leave, right? It's already 5:45, but I still have half hours more today. And actually, I need to move to another room, right?